Hello and welcome back to Level Up Rugby. Today, using the knowledge we've acquired in the previous video of what a sweet strike actually is, how you achieve it and why it is important that you achieve it, we're going to be deciphering where the sweetest strike is actually made. So now we can quantify what a sweet strike actually is, where an indent into the ball's surface causes the ball to move itself away in the opposite direction to the object disturbing it, hopefully towards the post. This now poses the question of where on the ball's surface the largest indent and therefore the sweetest strike is made. And linking it back to the stage of the process we're currently working on, which style of kicking tee you should pick. Okay then, so there are two commonly known sweet spots on the ball. The first through the vertical axis of the ball, going from point to point, and the second being slightly higher than commonly thought, running through the horizontal axis of the ball. Now then, what makes these two spots the sweetest to strike as opposed to other places on the ball? Well, unlike other places on the ball, if you strike in the most efficient way, a straight line, through and along these axes, then the ball will push itself away from your foot back along that line towards the posts. On the other hand, if you strike and indent the ball in places other than these two sweeter spots, for example, down at the bottom of the ball, like most upright tee kickers aim for, the ball not only has a shorter length to indent upon, but as you can imagine, if you strike and indent along that line, the ball will only push one half of itself away, as opposed to its whole self, causing the ball to have plenty of backspin, but no real forward direction. Okay then, so now we have our two contenders. Which sweet spot / axis provides the largest indent and therefore the sweetest strike? First, we must consider the length through the ball that each axis provides our foot, so it may travel the furthest into the ball, therefore creating the largest indent. As the shape of the rugby ball determines, the vertical axis provides us with the longest distance to indent upon, especially in comparison with the horizontal axis. However, although it may provide us with the greatest potential distance to indent upon in theory, the variable that we are actually comparing between in practicality is the achievable indent size of each axis. As we discussed in part 1, after the combination of the amount of pressure that your foot creates by condensing the space for the air particles to move around in, and the time that the ball is under pressure for, the more the ball will want to return to its natural shape. So therefore, the practical amount of pressure you are able to create depends heavily upon the length of time it takes to create it. The further your foot travels into the ball, in terms of distance, assuming ceteris paribus with regard to foot speed, as I'll be getting onto, means the longer the ball is under pressure for in terms of time. And the longer the ball is under pressure for in terms of time, the sooner it will want to return to its natural state. As you can see, if I wasn't holding onto the ball and tried to indent it with my thumbs, it would instantly move itself away without the chance for me to even make an indent, just the same as a solid would. However, when a solid object travels at a much faster speed, say for example, the speed that your strike foot travels at, it means the ball is almost caught off guard. This is because of the space between air particles as opposed to the lack of space between particles in a solid. But like we said, after time, the ball will notice something disturbing it, causing its pressure to build, and it will want to return to its natural shape, therefore concluding that the largest indent that you can make in the shortest amount of time under the practical limitations of how fast you can actually swing your foot will win the title of the sweetest sweet spot. The shorter distance of the horizontal axis means that in the given time before the ball reacts, your foot is able to travel further along the horizontal axis, creating an indent much closer to the ball's potential before the factor of time kicks in and the ball returns to its natural shape. On the other hand, the vertical axis, like we said, is a lot longer than the horizontal axis, meaning that to cover the longer distance of the vertical axis in the length of time before the ball reacts, to achieve the same amount of pressure and volume as the horizontal axis, your foot would have to be travelling at speeds faster than humanly possible. And what is my evidence for this? Well, have you ever seen the ball be indented further than a quarter of the way along the vertical axis at the most? Unfortunately, you cannot swing your foot at a fast enough speed to build the maximum potential pressure inside the ball to initiate that factor to reject the foot. This is because the other factor that causes the ball to regain its natural shape of time under pressure kicks in first. The time that the ball is under pressure for kicks in before the effect of the ball reaching its maximum physical pressure limit that it can take. This is because you cannot swing your foot at a fast enough speed into the ball to achieve the maximum amount of pressure the ball can take before the ball starts to move itself away from your foot. This is why the theoretical advantage of the longer vertical axis proves to be its downfall with regard to practical, achievable indent size. This is because the length that your foot must travel into and along the vertical axis to build the same amount of pressure and volume of indent into the ball as the horizontal axis is not possible in the time before the ball reacts due to the physical limitations of the speed that you can swing your foot at. To translate this back across to our trampoline analogy, the gymnast's initial jump off the trampoline gains him height, and then because of gravity, it then generates speed back down into the trampoline, in the same way that your foot generates speed to travel into the ball. As we see the gymnast gaining more and more height through the utilization and maximization of all potential energy supplies, as we covered in the last video, we can see that he eventually maxes out at a certain height. This again is because of one of two factors. Either he has utilized the full potential of the trampoline, and if he was to create any more tension in that trampoline in the slightest, it would just snap. Or the speed he is traveling at back down into the trampoline is not fast enough to reach the maximum tension before the other factor of time under tension forces the trampoline to push him back into the air. Taking this analogy back to the ball, either the ball can't take any more pressure being built, so it initiates the moving of your foot away, or else it will pop, or your foot speed is just simply not great enough to achieve that maximum pressure before the ball decides to go back to its natural shape. So again, this demonstrates why time, because of the limitations of your foot speed, is causing the downfall of the once thought strength of the length of the vertical axis. You can only steal so much space into the ball before the alarm bells start to ring and the ball returns to its natural shape. So therefore, the more indent that you can steal before the alarm bells start to ring, the larger your indent will be. But we know that you can only swing your foot so fast, you can only steal so much so quickly. So for this reason, the shorter length of the horizontal axis allows your foot to travel further into the ball, to steal more indent before those alarm bells start ringing, as opposed to the vertical axis. Sticking with the trampoline analogy for a minute, the second reason why a Sweetest strike comes from the horizontal axis is because of the increased surface area of the location to absorb the foot and allow the indent. The vertical axis is much more like a trampette, a small trampoline, and the horizontal axis is much more like an Olympic trampoline. You cannot achieve as much height on a mini trampoline because of how tense it is. You can only sink so deep into it before it either snaps because you have maxed out its much more limited spring potential, or it forces you back up into the air, like we've previously said. The same goes for if you overinflate your ball, as I'll be covering in the next part of this series. However, the increased surface area of the big Olympic trampoline allows you to sink so much deeper into it without it breaking or forcing you back into the air so quickly because of its lack of tension. To translate this again back across to the ball, the vertical axis is the small trampoline, only being able to take a small amount of tension before it wants to regain its natural shape or break, therefore not providing a great amount of spring, i.e. indent, before it pushes back. On the other hand, the horizontal axis is more like the big Olympic trampoline because it can take so much more tension, i.e. pressure, of your strike foot into itself, indenting it before it wants to push back or break. So to conclude, for these two reasons of the shorter distance to steal a larger indent before the ball pushes back, and the larger amount of pressure the ball can take over the larger surface area of the horizontal axis, we crown the horizontal axis the winner of the sweetest sweet spot. But the story isn't quite finished there.